بسم الله الرحمن الرحيم، والصلاة والسلام على رسول الله وعلى آله وصحبه أجمعين. معكم طارق الرشيد، وهي تدريس في قسم علوم البحار، وعضو في وحدة الابتكار والتعاون الخارجي. في البداية أرحب فيكم في المحاضرة الثانية من سلسلة محاضرات برنامج الانوفيشن توكس المنظمة من قبل الوحدة، ونشكركم بالمشاركة سواء من خلال حضوركم الشخصي أو عن طريق استخدام منصات التواصل المرئية. إن شاء الله محاضرة اليوم راح يلقيها علينا الدكتور فهد السنافي بعنوان الأمواج البحرية الكويتية تحت سطحية. بس قبل أن نبدأ لو تسمحوا لي نقدم نبذة بسيطة عن الدكتور فهد. الدكتور فهد حصل على شهادة الدكتوراه في سنة 2015 في تخصص الأوشنوغرافي من جامعة تكساس، وحاليا يشغل منصب رئيس قسم علوم البحار. كذلك يعتبر الدكتور فهد من أصغر الباحثين والناشطين في تخصص فيزياء البحار، وأوعدهم في المنطقة العربية، حيث قام في دراسات عديدة ميدانية مختصة في دراسة الاضطرابات البحرية وحركة المياه المسؤولة عن تحريك الملوثات والرسوبيات البحرية. عمله البحثي يركز على ديناميكية السطح البيني للجو البحر، ألا وهو الاير سي انتراكشنز. كذلك يشمل العمليات الفيزيائية ذات الطابع الدقيق صغيرة الكتل المائية، العلاقة بين الاضطرابات البحرية والأمواج التحت سطحية. كذلك بحثه شمل تطبيقات التقنية ذات الطابع الحيوي المختصة في الأغشية الحيوية البحرية. إن شاء الله راح يكون في هنالك فترة الإجابة على الأسئلة، راح تكون من الأونلاين أو من الحضور الشخصي هنا. فليتفضل دكتور فهد لقاء المحاضرة.
Thank you, Dr. Tariq, for the kind introduction. First, I would like to thank Dr. Intisar al-Madahka for making arrangements for this presentation. My talk today is about the subsurface waves in Kuwait, exploration and applications. Usually, before I start my talk, I present a phrase, an inspirational phrase to motivate people into the field of science. And I couldn't find a better phrase than the verse from the Holy Quran, أو كظلمات في بحر لجي يغشاه موج من فوقه سحاب, from Surah An-Nur, verse 40. This to me is one of the miracles, the scientific miracles in the Holy Quran, that actually explains that we do have internal waves, and this has been written in the Quran more than over 1400 years ago. So this by itself is a miracle, I believe, is a strong miracle, because such internal waves cannot be seen by eye. They can only be detected through specific instruments, and only can be seen through satellite imagery. To begin my talk, I'd like to start with the aim of my work and why I did perform it. The goal of our project was to advance our understanding of the characteristics of internal waves and the associated multi-scale energy cascade from internal waves down to turbulence on the continental shelf of the northwestern Arabian Gulf off the coast of Kuwait. So what does that mean in plain English? We wanted to detect these internal waves. We want to learn about their size, their speeds, their wavelength and height. And most importantly, we wanted to know the energy budget. How much energy is being produced by these internal waves, and how much of that energy is being dissipated into smaller scales, and at the end it would affect the marine environment. So that was the overall aim, and I'll return to the overall aim in my next few slides. The content of my talk today will be talking about the regional and infrastructure background, which briefly states why our study is important for the region here. The second part is giving you a brief scientific background about these internal waves, how they are, or the definition of internal waves, and how they are generated. The third, we'll be talking about the methodology of how we did perform our field work. Then it's the results section, and finally the conclusions. The results section is very brief. We chose a couple of figures due to the lack of time in my talk today. So to start with, I'll be talking about the regional infrastructure. Most of us know this kind of information, but it's good to repeat it. The Kuwait population, mostly, or 84% of the Kuwait's population resides within 10 kilometers of the coastline. This is crucial because all that population is adding new challenges to our marine environment. And the Kuwaiti population has increased over double in the last 20 years. So as the country continues to develop, we get more infrastructure being built along the coastline. And all that adds to the marine environment challenges that we need to take into consideration. And to understand these challenges, we must understand the dynamics of the Arabian Gulf. Kuwait is a country that heavily relies on petroleum exports. That accounts to 70% of the income. Kuwait is the 10th largest producer of oil, around 4 million barrels per day. To diversify its economy, the Kuwaiti government and leadership came with the 2035 vision of New Kuwait. This ambitious vision aims to transform the country into a global financial and trade hub. So what does that mean? Kuwait will continue its development of its urban infrastructure along the coastline to meet the present and future demands on energy, water, and transportation. So if we look at those three phrases specifically, the energy, water, and transportation, we will know that the energy, the electric generation capacity of the 5 coastal power plants have increased from 15 gigawatts to 25 gigawatts in the last 5 years. In addition, the water production has increased from 682 million cubic meters per year to 729 at the 3 main desalination plants in Kuwait. So this is important in terms of our marine environment because the power plants and desalination plants, what they do, they intake the seawater, they use it as a coolant for their engines and to produce fresh water, and the excess water is discharged into the marine environment again. The characteristics of that excess water, it's usually hypersaline. And the hypersaline waters that is being discharged by these plants causes the marine environment to change from less salinity to more salinity. And this does have negative impacts on the marine environment, more specifically on the marine life and the nursing grounds. So this brings us to one of our main objectives of the study, which is to understand the dynamics of the Arabian Gulf. For Kuwait to develop its infrastructure, we should study the region first and understand the dynamics in the region so that the policymakers can make better decisions on where to place these desalination plants in future and not place them in regions where water is usually stagnant, like Kuwait Bay. Kuwait Bay, usually the waters there is more stagnant compared to the open Gulf waters. And having desalination plants there and power plants would further add to the marine environmental challenges in that region. And the third phrase is the transportation. As we all know, Kuwait just recently opened its 104-kilometer Sheikh Jabr bridge. This is the 4th longest bridge worldwide. This bridge is the aim of this bridge is to connect the future megacity, Silk City, which is the Bmedinة الحادية, to Kuwait City. This is the first step to connect the nation to the Silk Road economic belt to diversify Kuwait's economy. So one of the 2035 vision is to make sure that Kuwait is the center of the trade hub, which is connecting Kuwait to the Silk Road that connects Eastern Asia all the way to the Western Europe. And the Silk Road will pass through Kuwait and its ports. So this makes this region very crucial to us because the marine road is connected to the continental Silk Road here. And that's why Kuwait has developed its infrastructure, it's built its bridge, and will continue to build Bmedinة الحادية, which is the Silk City. This Silk City will be the center that connects the marine road to the continental road that connects Kuwait to the Silk Road. So all of this is crucial to us to understand the dynamics of the Arabian Gulf. A better understanding of the Gulf dynamics that will benefit policymakers in managing future development in coastal zones and the sustainability of its natural resources. Example, tourist areas, bridges, power plants, and ports. So we cannot build any infrastructure unless we do understand the dynamics in that region, so we don't have negative consequences on the marine environment itself. It's not just Kuwait that's been developing in the Gulf. The other countries have been developing as well. UAE, Saudi Arabia, Qatar, Iran, Bahrain, all the countries in the Gulf have been developing. And the demand in the region is growing. The Gulf includes 12 of the top 20 fresh water producing desalination plants. Again, these desalination plants do discharge hypersaline waters into the Gulf. And because of the Gulf dynamics, it acts as a flushing system that takes all that excess hypersaline waters that's being introduced into the Gulf and gets flushed out into the Indian Ocean. So for us to understand this flushing mechanism, we should understand the Gulf dynamics that helps stabilize the salinity levels within the Gulf itself. The Gulf is also vulnerable to multiple risks of any damage that could occur to its coastal infrastructure that may spill into one of the surrounding countries because of the cyclonic currents. So all Gulf countries are connected to each other, and the buildup of the infrastructure means that any damages to these infrastructure would eventually spill to the neighboring countries and other Gulf countries and the Indian Ocean as well. And most commonly known is the intentional release of oil by the Gulf during the Gulf War. Over 11 million barrels were being put into the Gulf waters that caused serious consequences that extended from Kuwait all the way south to Bahrain as well as UAE. So any damages that does occur to the infrastructure or any intentional release of pollutants into the water does affect all the Gulf together. So we must understand the circulation and the dynamics in the Gulf to better assess the situation of any environmental hazardous damages. It's also important to point out that Iran's coastal Bushehr nuclear plant was rattled by a 4.5 magnitude earthquake last year. And a week before that, it was also hit by a 4.9 earthquake. And it's also important to note that the UAE just last year commissioned its first nuclear power plant with 4 main reactors. So for us to better control any hazardous situation that may arise from any of these coastal infrastructures, we must understand the coastal dynamics that do occur in our Gulf waters. All of these facilities are susceptible to storms, high waves, and natural hazards, earthquakes, or anything of that sort. So any significant damages to these plants can lead to disastrous implications to all Gulf countries, and its influence may reach up to the Indian Ocean and global oceans. All the oceans are at the end connected, so any hazardous material being put into the Gulf will eventually find its way to the Indian Ocean, and from the Indian Ocean, it's connected to the global oceans. This brought us to our second objective of our study, which is investigating the Gulf dynamics that will allow better understanding of the main flushing mechanism of the increasing waterborne constituents such as hypersaline waters generated by plants and contaminants such as oil spills, industrial waste, and metals. Now I have explained why we have performed this study and the importance of it. Now I'll give a brief scientific background of what internal waves are. From a physical standpoint, continental shelves like the Arabian Gulf are complex environments that host lots of physical processes, which include barotropic tides, mesoscale and submesoscale variabilities, including eddies, currents, upwelling and downwelling, and just now, as we found out in our study, internal waves. Before this studies, there were no study in the published literature that talks about internal waves in the Gulf. So this discovery in our project will have massive implications on rewriting the physical oceanography in the Gulf region. So what are internal waves? Internal waves are analog of waves below the sea surface and propagate in any fluid with stably stratified density. So what does that mean? Usually in the field of fluid mechanics or even air dynamics, when we have two water bodies or two air bodies with different densities, we get an interface that develops in between them. And if we do have a disturbing force, that interface would isolate and or oscillate to become waves. If anybody goes to the beach, he will see surface waves. And the reason why we see these surface waves because there's an interface between the air and the seawater itself. The air density is different than the sea density, and between them is the sea surface, and that's the air-sea interface. And any disturbing force, like winds or tides, would result in the surface waves that we would see at the beach or any coastal waters. Now, internal waves do not occur at the surface. They are waves that occur in the subsurface, below the surface. So what happens usually in summer? The sun's rays heats up the ocean, The sun heats up the ocean so that it becomes a two-layer system. And a two-layer system would be that we have a top surface waters and a deep surface waters, deep water, sorry. And between those two water masses is the interface. And a disturbing force like tides or winds can generate these waves that would oscillate in the middle of the water column. So these are the internal waves that we wanted to detect and study during our project. And internal waves play a major role in the transport of momentum, production of mixing, and dissipation of energy in regions far from their generation. These waves can travel up to 1,000 kilometers, so they do travel long distances. Our main focus in this study is not just detecting these waves and understanding the characteristics of them in terms of their size and speed, but the energy budget itself. These waves do carry a massive amount of budgets. They are comparable to a surface wave that's 300 meters in wavelength and 18 meters in height. So imagine going on the beach, looking at the beach, and suddenly you would see a wave coming towards you that's 18 meters high, larger than any house, in addition to having a wavelength of 300 meters. So that's the comparison between the forces that would be generated by these internal waves and a surface wave that we would see on a sea surface. So these waves do carry massive amounts of energy, and as soon as that energy is being produced and dissipated into the marine environment, it would have a large consequences on the environment itself. So that was the main interest of our study. And as you can see on this diagram here, an internal wave is being generated, and as soon as it meets the coast, it gets broken, and all that energy that's being stored within the wave gets released into the environment. And that is the point where is the interest of our study, is to study how much energy is being released into the environment. As I mentioned, the forces or the energy released by these waves are massive, are comparable to a 18-meter height wave, sea surface wave that we would see along the coastline. Now, the methodology. How did we perform our study? We had 11 moorings spread off the coast of Fintas in Kuwait. We did place the moorings on a slope. As you can see here, the depth does increase as you go further off coast. We intentionally did that because we wanted to know where is the breaking point of these waves. Theoretically, these waves do break at a critical slope angle. So there's a specific angle along the coastline that they would break, which is related to the depth of that region. So in order to figure out the critical angle of the breaking point, we had to put moorings at a different depths. The moorings were perpendicular to the coastline, and also we did have moorings parallel to the coastline. The reason is we were not sure if these waves would propagate towards the coast or they would propagate in parallel to the coastline itself. So just to be safe, we had both dimensions covered. So what did these moorings contain? Each of these moorings contained multiple sensors, as you can see here in the schematic diagram. We included light sensors because part of measuring the energy budget, we have to know the light attenuation with depth or the light decay with depth. We also had temperature sensors. These are slow sensors that took measurements every minute. We had a CTD, which measures salinity, or from conductivity we get salinity and temperature. We also had fluorometers, because one of our interests was to look at how these waves do affect the chlorophyll levels in the water column. Another thing, most importantly, we had fast temperature sensors. These sensors could measure at a rate of 32 hertz, meaning 32 measurements per second. Our interest in this study, which is turbulent, the small scale dissipation of energy, in order to achieve that, we had to have sophisticated instruments that measure at a very high temporal resolution. These sensors, we managed to connect them to wings so that they will be always facing towards the current. Because if they weren't facing towards the current, we would be measuring the wake from the line itself or the instrument itself. So in order to make sure that all the turbulence being generated are from these internal waves, we had to make sure that these sensors will always facing towards the current. We also had dissolved oxygen sensors, which gave us the oxygen levels within the water column, because we believe that these internal waves, when they break, they do mix the water column, and part of the mixing of the water column would increase the dissolved oxygen levels within the water column itself. And we also included an ADCP, which is an acoustic Doppler current profiler, which gave us a vision of the current structure itself. So the currents, how did they move? So all of this being put together would give us a clear idea of how these waves do propagate and their, most importantly, the energy cascade from high levels to lower levels, or from large scale to smaller scales. So this is what we call, as oceanographers, a water plot. Each line here represents the density with depth. So that's during a specific timestamp. And this is the depth here. The depth of that waters were around 20 meters. The x-axis here is the time, and the period here is about a bit over 24 hours. And usually there is in the mid layer of that line, you would see a breakup of the line, which occurs here. This is what we call, as oceanographers, is the picnic line, which is the intersection or the interface between the upper level and the lower level, and the interface between them is marked by that picnic line here. And if we mark the depth of that picnic line, we could see how the picnic line oscillates up and down, and that's our internal wave. And we could see it oscillating during a 24-hour period. So from this, we believe we detected the internal wave, and we could detect its height, which is roughly about 5 meters in height, and it could become up to 10 meters at different time periods. So what happens to this wave? One of our main interests was the energy budget, what energy is being introduced to the environment. Here we use the fast temperature sensors that measure up to 32 hertz. And what we noticed is that from this spectral analysis is that we saw elevated spectral levels at specific time periods, and these time periods were during the peak moment of the wave crest. So they were like pulses of energy being released because of these waves as each wave passes by. So as soon as we would see a wave pass, we would find a release of energy. And another wave pass, we would see another release of energy. So a lot of this energy is being released into the environment. And this was detected through our fast temperature sensors that caused, you can see that the temperature being less constant rather than varying a lot during this time period. And that is because of the eddy or the turbulence generated by these waves when they do break. Everyone, I'm sure, been on a plane before and noticed the bumps during turbulence. These are the same turbulence that we would see in the water column itself. So a lot of emotion and bumpiness that happens into the water, and that bumpiness that occurs in the water column does result in the mixing of the eddy or the circular motion of eddies that would result in the variability of the temperature levels. Now, our next step is we want to know what generated these waves. What is the main mechanism that generated these waves? So what we did, we took the vertical velocity, because we believe that these waves move vertically, either up or down. And we again performed a spectral analysis to see at what periods they are occurring. And what we noticed is that we found elevated spectral levels at a peak of 24 hours, around 24 hours, and 12 hours, and 8 hours, and 6 hours, 4 hours, and 4 hours. And these peaks in spectral levels are similar to the peaks in spectral levels we see in tides usually. So in Kuwait here, it's pretty much a semi-diurnal tidal area, meaning that we have 2 high waters and 2 low waters. And that's why we see the 12-hour peaks. But we also have a 24-hour peak, which is related to the sun's location. So from this, we can conclude that these internal waves that have been detected are generated by tidal forcing. Now, in conclusion, this work offers the first detailed study of internal wave characteristics in the Gulf. There was no study in previous published literature that mentioned these internal waves. So adding this to science, I believe, is crucial in our region. It will help decision makers in planning the coastal area, the coastal region better, especially under the developing and under the new Vision 2035 new vision. These waves were detected through the changes of temperature, salinity, density, currents, turbidity, dissolved oxygen, and chlorophyll levels. I did not present all that results today because of the lack of time, but we did publish our work in the Journal of Frontiers in Marine Science, where all those are present in that publication there. The vertical velocity data revealed that internal waves actively closely followed the semi-diurnal and diurnal tidal cycles. So they pretty much followed the tidal cycle because they were the generating force. Internal waves had an amplitude ranging between 7 and 9 meters. So the waves here in Kuwait were 7 to 9 meters below these surface levels and did propagate at the speed of 0.31 meters per second. I believe that these waves can be used to generate energy rather than as a green method of energy because they do host a lot of energy themselves. And this concludes my talk. I thank you, and I'd like to thank KFAS for funding my work, and also Kuwait University for its research sector, and Texas A&M University who were part of this project. شكرا.